Hello, folks. Today, the topic for today is mathematical description of propagation. That means this video is all about waves. So, how to describe a wave? The equation that defines a wave. In special case when we have a sinusoidal or harmonic wave. So let me write the title, mathematical function. And first, let us consider this function z equal to f of x. The graph of these functions look like, or this case look like this way. So here we have this nice curve, and also here we have another curve, and somewhere we have another curve. Here is our function z equal to f of x. But here we have it corresponds to the same function, but with a displacement x minus a, that here this curve corresponds this function z equal f x plus a. So notice that the following thing that here the shape of the curve has not been changed, has not been changed. So in other hand, we have this function corresponds to a rigid displacement of the curve to the right. By amount of a, or only amount a. Sorry. Yeah, nice. So yeah, now if a is equal to b times t, where t is the time and b is the velocity of the wave, then we can get a traveling curve. Then we can get a traveling curve, and that is this function phi equal to f x minus velocity times time. So represents represent a curve moving to the right with velocity b, called the phase velocity b, call the phase phase velocity. Phase velocity. So therefore, we have a conclusion. Therefore, we conclude that a mathematical expression of the form z uh, sorry z depends on x and time is equal to f of x minus b times t is adequate for describing a physical situation that travels or propagate propagates travels and propagates. So this is called actually the wave motion. This is called the wave motion. But this is the general case. So more things that the quantity, the quantity, the quantity, z x t may represent, this is a fact, represent a great diversity of physical quantities. Such as the formation in a solid, the pressure in a gas, uh, an electric or magnetic field. So now we are interested in the special case that we have is in which sorry about that. Wow. In which this function z, this function z d xt is a sinusoidal or a harmonic function. This is and this are the one case. So the formulation of this case is given by this formula. This formula is xt equal, this is the amplitude times sine of k of x minus bt. This is our equation that models sinusoidal waves. So where k has a special meaning. So k in the next we are going to realize that the k is a wave number. So replacing the value of x by x plus 2 pi over k, we get for this expression equal the same value. The same value. That means replacing here sine k x plus 2 pi k minus b times c. It can be written as a sine k x minus bt n plus 2 pi. Yeah. And then it turns out that we have the same function. The same function x t. Because here we apply identities, trigonometric identities, that produce lies to the same formula. So the formula that we are applying here is that following. If you have sine of something plus b for something, any value. So this is equal to sine of a times cosine of b plus sine of the other angle b times the cosine of a. So in this case, when cosine of 2 pi is equal to, this is equal to 1. When cosine, for example, sine of 2 pi, this is equal to 0. Yeah. Next, we have that then lambda is equal to 2 pi over k is the space period. But also lambda is the where it's called lambda is called the wavelength. The wavelength is, I'm spelling wavelength. Then the quantity k is equal to 2 pi over lambda is the wave number. So good way is represent the number of wavelengths wavelength in the distance to pi, and it is called the wave number. Some books write is following thing, or k to 2 pi, which corresponds to the number of wavelengths. Wavelength in 1 unit of length. So therefore, the final equation for the wave motion for this case, we have x minus equal to the amplitude sine k times x minus bt. It can be written as amplitude, the initial, find 2 pi lambda x minus bt. If you are wondering why this formula, when it comes from, so it's easy to show that. For example, as we said, that sine of k b times t is equal to what? Sine of 2 pi lambda x minus bt. This is equal to what? Sine of 2 pi. That is that is k becomes 2 pi over lambda. So that is. So and of the publicity. Now continue with what we are with our interest is this wave is called two stars. Two stars represent a sinusoidal or harmonic wave of wavelength lambda propagating to the right along the positive x-axis with velocity v. So therefore, our final equation is t is equal to the amplitude times sine of k times x minus the angular frequency times t. So where W R in this case is let me see, it's omega is equal to 2 pi b. This is the velocity over lambda, the wavelength, gives the angular frequency of the wave. But also, you can remember that the angular frequency is equal to 2 pi and b times the frequency. But in other books, you can find 2 pi frequency times f. That means it's frequency, the normal frequency. So b is the frequency you see with which with which the physical situation varies at every point x. So we have an important relation that is important relation because it make a connection is a connection between the velocity and frequency and also the wavelength. So where velocity is equal to lambda times frequency. So if P is the period, yeah, if P, this is nice. So if P is a period of oscillation at each point, then P is equal to 2 pi over the angular frequency. But if we replace here 2 pi, this is 2 pi times velocity times the wavelength. Then we have that 1b over the wavelength. That is the frequency. That is the frequency. That is the frequency. That is the frequency. So now this equation can also be written as x over lambda minus c over p so since this formula comes from because first we have, that we have this formula. Sine 2 pi over lambda b minus x minus bt. So if we actually this is wrong, it's 2 pi. So now if we make the distribution here, and we know that yeah, we know that sine of 2 pi um 2 pi x over lambda minus b over lambda t. If we this is one, and make this, yeah, actually I don't know what is something is wrong, something is wrong, something is wrong. I don't know why. This is lambda is good. This is k. But actually this formula can be written 2 pi x lambda minus t over p. Here's something, here's the problem. Here's the problem. We have to find a solution for this. We have b. Let's see if it's correct. Yeah. This is actually right. Yeah, it's easy to show that. I was wrong here. Sorry about that. I was wrong. If you put k, b with x minus wt, this period can be written as 2 pi over w. That means if we multiply by 1, this is 2 pi over 2 pi. Wow. I don't know what happened today. 2 pi this. This is t. So it's not right. It's 2 pi over 2 pi 1 over 1 this. But this is can be, this is the period. So yeah, that is, I was mistaken, sorry. Okay, it's 2, but this is 2 over lambda b minus 2 pi times period and sine 2 pi times x lambda plus times over p is equal to this one. So move on to the next. We may note that while the physical situation propagates to the right, it repeats itself in space. After one period. But what is the reason here? What is the reason? The reason. So the reason is because lambda is defined as velocity over frequency. That means that velocity times the period. So the wavelength, that the reason is, the reason is because the wavelength is defined as the distance, the distance advanced by the wave motion in one period. The distance advanced, that is, by the wave motion in one period. So that is the reason. Now, therefore, in sinusoidal, make wave. Therefore, in sinusoidal wave motion, we have two periodicities. We have two years. One in time and other and given by P and 1 in space given by the wavelength. Wavelength lambda with the two related by lambda equaled velocity times the period. The two related by this expression. So finally, an example, a tuning fork, a tuning fork oscillate with a frequency of 414 hertz. If the velocity of sound in air is 340 meters times seconds. Find the wave length of the sound. So now solution is so easy. This example, we are given with the frequency of the tuning fork and the velocity. So now by the equation we have the lambda is equal to, we are asked for the wavelength. So lambda is equal to the velocity over the frequency. So the velocity is 340 meters minus 1 over 440 hertz. So that is equal to sound quantity. Also in units of meters, in meters. So that's all for today. Thank you.